Hello and welcome to Autumn 1 Week 5 of marking the Year 10 exam, Newton's Laws of Motion. Remember, you need with you your green pen for making corrections, your blue pen for making any annotations. Right, let's get started. So, Newton's Laws of Motion. Question 1 says, Figure 1 shows a worker pushing a crate across the floor with a force of 60 newtons. Here we are pushing the crate with a force of 60 newtons. The crate moves at a constant speed in a straight line. Draw an arrow on the diagram to show the direction of the friction force acting on the moving crate. Now the key thing I want to take out of this question is it says it's moving at a constant speed. And this is where we can bring in Newton's first law of motion. Which says that if something is moving at a constant speed and constant direction, that means the resultant force will equal 0. So here we have a crate moving at a constant speed. That tells me the resultant force is going to be 0. So the resultant force, the sum of all the forces acting on that crate. So we've got 60 newtons pushing in this direction and the overall force needs to be 0. The arrow that I'm going to draw on my diagram is going to be going in the opposite direction, and I'm going to try to draw that arrow roughly around the same size. 1 mark there. State the size of the friction force acting on the moving crate. So the overall force, the resultant force, is 0. If I have 60 newtons going this direction, in the other direction I must also have 60 newtons. 1 mark for that. Give a reason for your answer. The resultant force must be 0. Okay, let's go to our next question. Calculate the work done by the worker to push the crate 28 meters. Now remember, the crate was being pushed with a force of 60 newtons. Show clearly how you work out your answer and give the unit. Choose the unit from the list below, and they've given us joule, newton and watt. Okay, first thing I'm going to do whenever I'm answering one of our calculation questions is list my values. So I'm trying to work out work done. That's going to be something, and that's going to be in the units joules. My force, I know up here my force is 60 newtons, and distance, that is 28 meters. The equation that combines all of these values is work done equals force times distance. Now I need to substitute in my values. 60 newtons times 28 meters, and it gives me an answer of 1,680 joules. I'm going to pop my answer down here as well. I get 1 mark for substituting in my values correctly, 1 mark then for getting the right answer, and another mark for selecting the right unit, which is joules, capital J. 2a shows the distance time graph for a person walking to a bus stop. Here I have distance on my y-axis, time in seconds on the x-axis. We can see their distance is increasing, then the distance stays the same for a short amount of time, and is increasing again. Which one of the following statements describes the motion of the person between points R and S on the graph? Not moving, moving at a constant speed, or moving with increasing speed. So here between R and S, these 2 points, if I just go across on my graph, I can see that the distance is staying at 300 meters. So if you imagine you'd run around a running track 300 meters and then you stayed there for 50 seconds, what would you be doing? well, you would be not moving. Okay, 2AII. Another person walking at a constant speed travels the same distance to the bus stop in 200 seconds. Complete figure 3 to show a distance time graph for this person. So, I've got distance in meters and time in seconds. I'm travelling, if I look back at my graph from the previous question, a distance of 500 meters. And I'm going to do that in 200 seconds, it says here. So, I'm starting at my origin, 0 meters travelled in 0 seconds. I'm going to travel 200 seconds here and 500 meters. So I know I'm going to have a point here. Got 2 points. I'm going to draw a nice straight line between them. How do I know that's a straight line? Because constant speed is always a straight line on a distance time graph. So if you ever see constant speed and having to plot some points on a distance time graph, you know you're going to be drawing a straight line. Okay, next question, 2B. A bus accelerates away from the bus stop at 2.5 meters per second squared. The total mass of the bus and the passengers is 14,000 kilograms. Calculate the resultant force needed to accelerate the bus and the passengers. Now, to calculate this question, I'm going to use Newton's second law of motion. We've already mentioned his first law. We're going to look at his second law, which tells us that resultant force, that sum of all forces acting on an object, is equal to the mass times the acceleration of that object. So we can simplify that down to F equals M multiplied by A, and that's the formula we're going to be using. So we have a look at my question. Again, I'm going to list my values. I'm trying to work out the force. Don't know what that is yet, so I'm just going to put a question mark and newtons. The acceleration, 2.5 meters per second squared, and the mass, 14,000 kilograms. Now I'm going to state my formula that links those three values. Substitute in my values, and I find that force comes out as 35,000 newtons. Again, I get 1 mark for substituting in the correct numbers, another mark for calculating 35,000 newtons. Okay, figure 4 shows a boat pulling a water skier. There's a speedboat, here's our water skier on the back. The arrow represents the force on the water produced by the engine propeller. Here's our force arrow here. This force causes the boat to move. Explain why. Okay, to answer this, you need to understand Newton's third law of motion, third of 3. And Newton's third law of motion says that when two objects interact, they exert on each other equal and opposite forces. So what that means really is if you're exerting a force on something, it's going to push back with a force that's equal and opposite. So as I push down the table, where we say with 10 newtons, the table is pushing back with 10 newtons in the opposite direction. So we're explaining why here this force causes the boat to move. Our first mark is for saying that there is a force from the water onto the boat. So we've got a force from the water pushing onto the boat, and you get a second mark for saying that this force is in the forwards direction. So effectively what I've got is a force from the boat pushing onto the water, and because of Newton's third law of motion, I know there's going to be a force pushing back against that is equal and opposite, and that's going to push the boat forward. Okay, the boat accelerates at a constant rate in a straight line. This causes the velocity of the water skier to increase from 4 meters per second to 16 meters per second in 8 seconds. Calculate the acceleration of the water skier and give the unit. Okay, so again, one of my calculation questions. I'm going to state my values. So A is what I'm trying to work out. Not sure what that value is yet, but I know the units are meters per second squared. Time, looking up here, is 8 seconds. And I've got two different velocities here. I've got what I'm going to call U and V. U is the initial velocity, the velocity it was at the beginning, which is 4 meters per second, and V, which we call the final velocity, so the velocity it is at the end, 16 meters per second. Now I need to state my formula that's going to link them all together. My acceleration formula is acceleration equals that final velocity, V, minus the initial velocity, U, divided by time. So acceleration is the rate of change of velocity, so how quickly the velocity is changing. If I substitute in these values, I'm going to put in 16 minus 4 divided by 8. So acceleration is going to equal 12 over 8, and that comes out at 1.5. And my units, meters per second squared. So I'm going to get 1 mark for substituting in my values correctly, 1 mark for calculating the correct value, and 1 mark for the correct units, meters per second squared. 3BII. The water skier has a mass of 68 kilograms. Calculate the resultant force acting on the water skier whilst accelerating. I'm calculating resultant force. I have mass, I have acceleration. That tells me I'm going to be using Newton's second law, aka F equals m times a, that we used a moment ago. So calculation question, again, state my values. The acceleration, I know up here, is 1.5 meters per second squared. You may have calculated a different value if you got 3B incorrect. That's okay, you can still get the marks in this question. M equals 68 kilograms, and my resultant force, not too sure what that is yet. I'm going to put question mark newtons. Okay, so you should have your values listed. This might be a different value for you if you've got 3B incorrect. Okay, I'm going to put my formula that links the two together. F equals m times a. F equals 68 kilograms times 1.5. You may have a different value, remember. If I multiply those together for me, that comes out at 102 newtons. 2 marks, 1 mark for correct substituting in the correct unit, the correct values, apologies, and 1 mark for calculating the correct answer. If you got 3B incorrect, you can still get both marks if you have correctly substituted in your answer from 3b and you've done the correct calculation. So maybe you got 2.5 here. So if you did 68 times 2.5 correctly and you got the answer here, then you can get 2 marks. Okay, 3bii. Draw a ring around the correct answer to complete the sentence. The force from the boat pulling the water skier forwards. So we've got our boat and our water skier in this question. The force from the boat pulling the water skier forwards will be less than, the same as, or greater than the answer in part BII. So your resultant force that you worked out down here. The answer is it will be greater than. And given the reason for your answer, let's just focus this. Given the reason for our answer, it's because the boat needs to overcome resistance forces. So as that boat is trying to pull that water skier along, it not only needs to pull the water skier along, it also needs to generate a force to overcome the resistance from the water and the resistance from the air as well. 4a. Figure 5 shows the horizontal forces acting on a swimmer. Here we've got forward force T and a resistance force D. The swimmer is moving at a constant speed. Again, so as soon as I see constant speed, I'm thinking about what we said about Newton's first law of motion, that if the object is travelling at constant speed, the resultant force, the sum of all the forces on the swimmer, must equal 0. Let's just make a little note of that again. Okay, so the force T is 120 newtons. What is the size of force D? I know the resultant force needs to be 120, so if 120 in this direction, then that tells me I must have 120 newtons for D. 1 mark there. Okay, 4b. A sports scientist investigated how the force exerted by the swimmer's hand against the water affects the swimmer's speed. So obviously the swimmer is using his hand to push himself forward, and that's going to affect his speed in some way. The investigation involved 20 males and 20 females swimming at a fixed distance. The sensors placed on each swimmer's hand measured the force 85 times every second over the last 10 meters of the swim. The measurements were used to calculate an average force. So they're measuring force 85 times every second, and I'm going to calculate an average. The average speed of each swimmer over the last 10 meters of the swim was also measured, and they've put this data on the graph. So we're going to see this graph that has the average force of the swimmer and the average speed of each swimmer. Let's have a look. Okay. So I can see on my x-axis I've got the average force in newtons, and my y-axis the average speed of the swimmer in meters per second. And we need to look at our key. The small little x's stand for the male swimmers, the dot with the circle around it are the female swimmers. 4bi. What was the dependent variable in this investigation? Remember, whenever you get a question about independent or dependent variables, you can remember the chimed mnemonic. So that stands for CH, change, I, the independent. So we change our independent variable, we measure the dependent variable. So in this experiment, we're changing the force from the hand of the swimmer, and we're going to measure the average speed of the swimmer in meters per second. Another way I can remember this, apart from my chime mnemonic, is just looking at any graph. The independent variable goes on the x-axis, the dependent variable on the y-axis. So my dependent variable is the average speed of the swimmer. Okay, 4bii. Explain one advantage of measuring the force 85 times every second rather than just once or twice every second. By measuring our force 85 times every second, that means that when we're collecting data, we'll have lots more data. If you said more data, you can have 1 mark. And that makes our average that we calculate, so remember we had our average force and our average speed, the average is more reliable. And that's a really key term there, that the average is more reliable. 4bii. Give one way in which the data for male swimmers is different from the data for female swimmers. Okay, so remember we had on our graph our male swimmers here and our female swimmers with our dot with the circle around it. Okay, so I'm looking at my data and I'm thinking, what is the difference between the two? One difference you could have written down, I'm going to put down 2 possible marks. One is that most females produce a smaller force. If you'd written this down the other way around, so said most males produce a larger force, you can also have the mark. We can't say all females produce a smaller force, because if we have a look at our force here in newtons, we can see there are some females producing a larger force than males. So we need to say just most. If we look at the overall trend, most females are producing a smaller force than males. On a similar point, we can say most of the slower swimmers, or the swimmers with a lower average speed, are female. Again, if you've written that the other way around, so said most of the faster swimmers are males, you can again have a mark. If we just check that on our graph to see how we got that, we look at our average speed. These points that tend to be lower down on the y-axis are the dots with circles around them, the females, whereas the males tend to be higher up, have a higher average speed. 4biv. Considering only the data from this investigation, what advice should a swimming coach give to swimmers who want to increase their average speed? And you notice I've bugged this part, only the data. So you can't give advice such as, have a healthier diet or train more, things like that. We can only look at our data and what conclusions can we draw from it. And as I look here, I'm looking at this graph and I'm going to draw on it just a rough line of best fit that goes through these points. And if we see, as the average force in newtons increases, so does the average speed of the swimmer. So we can call that a positive correlation. So if I want to increase the average speed of the swimmer, as a coach, I'm going to say to them to increase the force being produced by your hand. Okay. Question 5. A cyclist is travelling along a straight level road and the graph shows how the velocity of the cyclist changes with time. So for this question we have a velocity time graph, the other question was a distance time graph, where I have my velocity on my y-axis, time on my x-axis. Complete the following sentence. The velocity includes both the speed and the direction of the cyclist. Why has the data for the cyclist been shown as a line graph instead of a bar chart? The reason for this is that both time and velocity both variables on my graph are what we call continuous data. So we have two types of data, continuous data. We also have a type of data, sometimes we see it being called discontinuous, but more commonly we see it being called discrete data. And that effectively is data that we can put into certain categories. So for example, something like shoe size or eye colour. We can only have these in distinct categories, whereas something like continuous data we can constantly break down into smaller categories. So for example, time is continuous data, so the time could be 5 seconds, it could be 2 seconds, it could be 1.5 seconds, 1.125 seconds, and so on. I can constantly break it down into smaller and smaller and smaller parts. Shoe size, your shoe size is either a 7 or a size 8. You can get a 7.5, but you can't get a shoe size 7.354. So this type of data, if I'm plotting it, discrete data, would be plotted on a bar chart, whereas continuous data on a line graph. Okay, last question. 5C. The diagrams show the horizontal forces acting on the cyclist at 3 different speeds. The length of an arrow represents the size of the force. So length is showing us size here. So here I can see there's a larger backwards force than forward force on A. B, again, on B, the forward force is larger than the backwards force, and on C, these forces are balanced. Which one of the diagrams, A, B or C, represents the forces acting on the cyclist when it is travelling at a constant speed, 9 meters per second? And again, I'm thinking constant speed, I'm thinking about Newton's first law, which means if something's at a constant speed, that means its resultant force must be 0. The sum of the forces acting on it must be 0. So I'm having a look here. We've got one force larger than the other, the resultant force is going to be 0. Same with B, whereas on C, with these forces being balanced, being of equal size and direction, that tells me this has a resultant force of 0. The forces are balanced, and so my answer is C. Explain the reason for your choice. In C, velocity is not changing. That's 1 mark. Our second mark is for saying that the resultant force is 0. And another way of saying that is we can say the forces are balanced.